Good. Marco, would you like to take us through the first item?
Yeah, sure. Okay, let me share my screen. Yep. So I guess it's just a sharing for what happened with we had some kind of regression on the Sidekick for self-managed users. So opening up the issue here. So what happened in 2 months ago, back in 15.4 release, we're trying to default the routing rules, whereby we wanted to change the default from queue per worker configuration to just 2 queues. One is default and one is mailers for typical self-managed users. So we deemed this was safe back then because the queue groups default in the Sidekick side are still star anyway. So we went ahead and deployed this. Then starting from last week, the support engineers pinged us basically. Ever since the release, there were a lot more Zendesk tickets regarding the bad performance. So what happened was that it's pretty much quite simple. So imagine you would have this queue groups. They already defined this previous to 15.4. So what happened then, this process are only processing or listening to certain queues except default. So then what happens for this guy case is the only running process is just this one. So the other two would just be idle. So that's what happened when they start to notice their Sidekick latency is getting higher. Yeah. So I've listed, these are some of the cases. So this was fine. And this was even more serious where you only have one process instead of 7, 8 here. Yep. So so basically that's what I mentioned. The root cause is just because they have defined a custom queue groups, and then we unknowingly assume that many people wouldn't use queue selector anyway. So there was a miscommunication there. And then, so then after they upgrade to 15.4, all the jobs are pushed to the default queue, and then some of the processes in Sidekick will become idle. Yeah. So actually, the fix is actually pretty simple. If they manage to contact our support, we already advised support engineers to. There are 2 ways. So first, they can still keep their queue selectors, but then we can kind of override the routing rules to become basically all jobs will be routed to the name queue again. So it will be back to the 400 plus queues. So this will be the previous state. Other than that, we can start to advise customer to, instead of using queue selector, we can now use routing rules. So for example, if they have something like this previously, then we can advise them, we can change the queue groups to in the routing rules format. So then they can define for this queue attributes, it will be routed to this urgent other queue and so on and so forth. Then in the queue groups, they can simply just define the specific queues they want to listen to for each process. Yep. So these are for the affected customers, but we also noticed that from the support tickets, there will be a few more customers that have yet to upgrade to 15.4, and there are some big names out there. So we don't want to have these breaking changes for them as much as possible. So our plan is that in 15.6, the upcoming release next week, 2 weeks or 3 weeks from now, we would be reverting the default routing rules. After that, we would also like to add this logic in the omnibus and chart so that we set this default routing rules for back to the 400 plus queues if they haven't set the routing rules and the queue groups only consist of stars. So this basically their default queue groups per se. So the whole point is that we don't want to mess up with their routing rules, the default routing rules, and whenever they already touch the queue groups. Then we also want to backport the first revert here to also 15.4 and 15.5 in case they, for whatever reason, they couldn't upgrade to 15.6. Yep. And then in 15.7, we want to reintroduce back the default routing rules. So basically unrevert the reverted change. Yeah. So yeah, that's about it. This is just a very quick sharing.
Mark, I don't know if I've missed something there. Thanks for sharing, by the way. That was a nice detailed walkthrough of the process. As of 15.7 then, does that mean we can then continue and go ahead and deprecate the old behavior, or are we waiting on customers or users to make changes to their configuration?
We would still need to first officially deprecate in the documentation. So we would still expect customers to still use the queue selectors before any major release. Yeah, so that's what I would expect.
Okay.
So I don't think by our discussion with Sean, it wouldn't be removed anytime soon for the queue selector. Yeah.
Okay, makes sense.
Are there any further questions on that one, or should we move over to Igor? All right, Igor, all yours.
Yeah, so admittedly a bit of a clickbaity title there. There's been a whole bunch of efforts around efficiency in Kubernetes, and some of the changes that have been made had kind of unintended consequences. In particular, putting more load on some of the shared resources. And just to kind of show some specific cases of that. So I guess one of the main drivers has been an increase in number of pods for our web service deployments. So that's API, Git, and web. And there's been sort of a few unexpected knock-on effects from this change. And so there were a few things around packing our workloads too tightly and sort of reaching CPU mid-level CPU saturations. But the one that I wanted to focus on is PG Bouncer. So we had an incident, actually two incidents related to PG Bouncer client connection limits. Let me see if I can find the second one. I think it was this one. Yes. So we have one for max client connections on our replicas, and we have one for the same thing on the primary. Our PG Bouncer setup is a little different depending on whether you talk to replicas or the primary. If you're talking to replicas, the PG Bouncers are co-located on the replica boxes themselves. So they share the box with Postgres, whereas for the primary, we have dedicated PG Bouncers. In any case, in both of those situations, we were approaching limits on the same metric, which is client connections. So PG Bouncer takes incoming connections from all of the clients. So that's going to be mostly Sidekick and web services. And these are a lot of connections because we have, one or maybe even more than one connection per pod coming in. And so it sort of does a fan in and then multiplexes that onto much fewer backend connections when it talks to Postgres itself. And that's because Postgres has kind of a pretty hard limit on how many connections it can support. So we need PG Bouncer to do this job for us. But each PG Bouncer process can only handle a certain number of incoming connections. And so going back to this, as we increase the pod count here, we're putting more connections into our PG Bouncers. And let's see, we can see a chart here. So this is, let me maybe open the actual chart if I can get it to load. And it looks like it's not loading. Not sure what's up with that. But it's our saturation ratio for how many connections PG Bouncer can handle, and we were awfully close to the limit. Actually, I think we even hit the limit in the end, which then caused some user-facing impact because they get 500s because the pods can't connect to Postgres. So this is not good, and there's a little bit of tuning and tweaking that we can do to this limit. But the broader question is, we in Scalability are projecting our usage over time and sort of capacity planning. And when we make changes to how the infrastructure runs, that can actually drastically change the usage. And I've been sort of thinking about how do we approach this in a better way so that we can better predict the outcome of those types of changes, right? So that when we make a change like that, where we're seeking to gain more efficiency, what will the other consequences of that be? Will we create more load on some other upstream systems? Is this going to put more load on PG Bouncer? Is this going to put more load on Postgres? And I'm not faulting the engineers who were working on those changes, because I think it's more a question of, do we have the mental models for that, and do we have the tooling to maybe kind of try and visualize that? And
can I ask a quick question? So
go ahead.
So the increasing the pods increased how many connections needed to be made. Is increasing the pods something that an engineer chooses to do, or is that like an automated thing that just when a certain level of usage is achieved, it automatically creates new pods?
Yeah, so we use horizontal pod autoscaler for all of our web service workloads. And so that means we configure, we've got kind of two variables that affect how many pods we get. We have the utilization target, which we set on the horizontal pod autoscaler, and we have the CPU requests. And CPU requests kind of affect how big is each pod. And the utilization target is relative to how big it is, how much do we fill it up? And both of those sort of indirectly, based off of the dynamic behavior, result in getting more or fewer pods. And so maybe to illustrate this, because that's kind of the main thing I wanted to show. so I've been putting together, this is still kind of early stages, but I kind of try to put together a diagram to show some of these interactions. And this is sort of a model, if you will. So we can sort of look at this and try and reason through some of the scenarios. There's a good chance that there's stuff missing from here, right? This is an abstraction. This is sort of simplified, but let's say we want to increase efficiency. And so maybe we raise the target CPU percentage.
So
where it was previously.
When you say efficiency,
Go ahead.
you want to increase the efficiency of?
The efficiency of resource utilization on our fleet, and effectively reduce the number of resources that we need. So operational expense, I guess, is sort of what it comes down to in the end, right? So if we were to, say, increase this utilization target, that means we drive each one of these pods harder. They have now, each one has more work to do. Presumably, you know, each one of them will be able to actually do that work. And so if that works out, then the same incoming load, the same incoming requests that we get will be spread across fewer pods. And so we can see, you know, CPU per pod percentage-wise goes up, pod count goes down. However, this has other potential consequences, because now each of these pods is running hotter. So that can increase sort of the contention on the host. And it can also affect the contention of the Ruby global VM lock. Because we're now, so Ruby global VM lock is based on how many processes you have per pod. That's the Puma was tunable. And so we didn't change this. So this stayed the same, but this went up, which means the CPU to Puma ratio changed in a way that each Puma worker is now doing more work. And that then drives this contention metric. So, yeah, it's complex, right? It's kind of the point that I'm trying to make. And it can be kind of tricky to really predict what exactly the effects are. Even with something like this, we can sort of try and reason through it, but chances are we'll get it wrong. So I think there's also an element of scientific method involved in making these types of changes.
And everything that you're describing here sounds very similar. I mean, it's similar in terms of class of problem to when we were trying to decide, I think it was it the connection pool size for the database? And it felt like we would do a certain amount of reasoning through the problem. We would set it, we'd get it wrong. And then we would do another set of reasoning and then set it a different way and see what that did. And it seems like what you're talking about here is the same class of problem where there's only so much reasoning we can do, and we're going to have to set them and see what happens to see how that actually plays out when it's on production.
Yeah, I mean, I think we can also use those experiments to refine our models. So we can, you know, we can potentially get closer to being able to actually predict it. But yes, I think it's very much in the same realm as what you described.
Mm.
Will a kind of copy of production environment where we could run synthetic tests with load, would that be a reasonable approach, or is the volume and number of moving parts so massive that it becomes impractical?
I think the problem with completely replicating a production environment is also cost. I mean, the production environment is rather large. And if you had an exact copy of that and running synthetic tests on it, I think it would become quite expensive quite quickly.
Right.
Yeah, I think it's also just technically pretty challenging to do. Like you either do synthetic load, and then you're likely not going to match what is actually happening in production, or you try to replicate real production traffic, and then you have the question of how do you deal with state changes and writes, because those are kind of tricky to replicate in a way that you can really replay it properly, because you get sort of out of order effects and whatnot. So I'm a bit of a skeptic when it comes to that approach, I guess. One approach that I do think has also some limitations, but can be pretty effective, is doing it on a subset of, making changes on a subset of the fleet. And that's what we're doing right now. So we have the 3 zonal clusters, and we're making the change in only one of the 3. There's still potentially some sort of interplay between them. So I don't think this solves necessarily for all combinations of changes. It could still kind of tip over once we roll out to everything, but it gives us at least a bit of an idea of how the changes are behaving in a way that sort of mitigates some of the risks.
Yeah, and that seems reasonable to
I don't
do,
think it's
if it's being done in a controlled way, and there's a plan for, if we see these certain things happening when we're making these adjustments, then we alter the plan and change it in that way to keep the system safe. But it seems like doing these experiments on production seems a reasonable thing to do. It seems like it's the easiest way to see exactly what will happen on production is to change it, just doing it within a risk tolerance.
Yeah, I think that's very much like the embracing failure thing that we've discussed before, but obviously controlling failure at the same time. Igor, I don't know if this is what you were describing in the drive diagram or something different, but is it possible or feasible that like our auto scaling strategy is dependent on certain hard limits in the system? And I guess what I mean by that is a common problem, right? That when you're scaling, you basically move like a bottleneck further down the stack. And is that something that's possible, so that our, like the pods in this case, wouldn't kind of grow out of control because they're aware of like certain static hard fixed limits that exist in the system?
I think it's a really tough one to solve in such a dynamic environment. I mean, the question is, what do we do if the pods are at 100% utilization? And so I guess one answer to your question is, yes, we have some controls on how far we scale out. So for the horizontal pod autoscaler, we have min and max replicas. And so that places an upper bound. It's not necessarily directly informed by what upstream limits might exist. I mean, we can sort of model those upstream limits and say, this depends on number of pods times number of Puma workers per pod, and then we set the limit accordingly. So, that's something that we could sort of semi-statically calculate and then set. But I think even if we were to do that, it just means that the pods won't grow to a certain, like above a certain limit. But once we reach that limit, those pods are still, they're still having a bad time, right?
But
Yeah,
that's
I
the
guess there's
problem
still
with
unknown. So we don't necessarily know the relationship between kind of pods and every other part of the like web, for example, and every other part of the system. Sorry, Rachel.
Well, what I was going to say is, I guess it's the problem with having like a limited arrangement with the database, because there's going to be there is a hard limit because there's only one writable database. And if you scale beyond what that database can handle, everything's going to have a bad time. But at some point, that limit gets reached, and it's a case of, well, what do you do at the point that limit is reached? That's
Yeah.
Yeah, I
Well,
guess
I
this is where it
suppose.
comes back to like the saturation forecast, right? Which, as I think like the demonstration, it's like that's the way that we work, and it works until it almost doesn't, right? When you kind of get a change that happens so quickly that the system starts behaving in a different way, which invalidates a forecast that we've made previously.
Yeah, so I think one other sort of orthogonal axis here is the isolation side. So if we think about sort of isolation patterns and patterns for handling overload, the two that come to my mind are bulkheading and circuit breakers. So bulkheading is effectively functional partitioning, or sort of partitioning by some kind of failure domain or some kind of group that you want to isolate. And so if we think about the database, if we had maybe dedicated PG bouncer nodes or dedicated PG bouncer pools, we can allocate them with fine-grained and say this group of pods can only use up to this many connections. And if it tries to use more, it'll break, but because it's a shared resource, it'll not affect the rest of the consumers. So there's sort of that kind of overload protection there. And then circuit breakers are really for, if we do reach overload, how do we deal with that in a way that we can recover from it? And so it's more about detecting that the upstream system is not able to respond and kind of having the clients back off. And so that can also help kind of stabilize during situations where that overload does occur. Yeah, that's more or less what I wanted to share. I don't have any real conclusions just yet, but it's something I've been thinking about, and I do think it's kind of relevant to what we do in scalability. So yeah, wanted to share that.
Yeah, thanks for taking us through it. Just heading back to the agenda. I don't see that anything else is there yet. Is there anything else anyone would like to demo or chat about? Alrighty, well, thank you so much for joining the call. Thanks for the conversation. I'll upload the video, and hope you have a good rest of your day.